Hello, everyone, and welcome to devOSH Live. Today we have a special episode. We're bringing in Tim Mithro, Ansell from wafer.space to talk about his new company and the shuttle that's just launched. There's on their third round of funding, and there's some new offerings, and it's been pretty exciting to watch all the things that they've been doing. So without further ado, I guess we can bring Tim onto the stage. Hi, Tim.
Hey, how are you?
Okay, good. So for anybody that doesn't know you, I guess the quick introduction, make sure that people,
Sure.
back.
I'm in mithro Ansell. I like to say I self-identify as a software engineer, and for like the last, I don't know, 6 to 8 years, I've been working on trying to make silicon more accessible for the average person, so that the average person can make their own integrated circuits.
Very cool. So I guess we could talk a little bit about the progression of the silicon offerings and kind of the history of the programs and where it started and how it got to where we're at today.
Sure. So I'm a software engineer, as I kind of said, and one of the things I kind of identify with being a software engineer is being a little bit arrogant and overconfident and thinking things are easier than they actually are. And so about 8-ish years ago, I started looking at what it would take for more software engineers to be able to make silicon chips. I started in the FPGA space. For people who don't know, FPGAs are kind of like silicon chips that can pretend to be other silicon chips, is the way I like to describe it. And then I got into the space of going, why hasn't open source really penetrated the silicon space? There's lots of theories about this, but when I look at the silicon space, I kind of see what the software industry looked like in like the late 1980s, early 1990s. You have to pay for your tooling. It's very expensive. There's no good open source libraries or any of these type of things. And so at that time, I was working at Google. Google was very concerned with the coming end of Moore's law type problem, and the idea that you needed software engineers to do a lot more chip design because they only care about exponential growth type systems.
Yeah.
When I got into the space, I discovered that there was a long history of open source tools. There was things like RISC-V, and before that, OpenRISC. And so there was some open source IP out there. And there was even a place called OpenCores, which was kind of like GitHub for hardware before GitHub existed. But there wasn't really any way to get your devices manufactured. And for silicon, that's like, I always use the analogy, trying to develop software without ever being able to run your programs. Like, you can compile them, you can look at the results, but you can never actually run them. Being at Google was kind of good in that it opened doors. And in the start of 2020, I basically open sourced a thing called the PDK for Skywater's 130 nanometer process technology. And the PDK is kind of like the fundamental information you need to actually make silicon chips that are really manufacturable. And the fact that that didn't exist really meant that like the tools and the IP could only be developed to a certain level because you could never really take them out and see whether they worked, right? And that's ultimately like, it doesn't matter how much testing you have, if you never run your program, it's probably not going to run, right? Like, and so that's kind of 2020. And as part of that as well, to get more people using the tools, Google also provided free silicon tape outs. And as part of that program, there were like 8-ish tape outs with each 40 projects on it. And then another 2 on a separate process technology that we'll probably talk about in a minute. But yeah, you have some history with that program, if I understand correctly.
Yeah, I was on the first shuttle with TNT. We did the Pi 5 project, or we were attempting to do some things with the Pi 5 project. First shuttle we did a tape out of TNT's. It was his USB core that we're trying to get working, and there were issues with the first shuttle, timing issues. And so that one thing that we wanted to test on that shuttle didn't actually work, but he did actually get some of the auxiliary cores working. He actually did some magic that brought the chips to life using a little bit of voltage tweaking. So I created a PCB, and it had like an FPGA, like a icebreaker board that plugged into it, and it would drive these regulators to change the voltages until the closure occurred on the chip, and we were actually able to see the UART and the video output and a lot of other things that were on there. Or the 3 other things. I guess there's only 3 things, but either way, seeing life from the chips was a really big deal because there were a lot of people that were upset. Hey, we can't do anything with our chips. And then we showed them, okay, we got life out of the first shuttle. Let's keep moving. Let's keep this thing going. Essentially, I thought it was a good. I think it was a good thing, and it helped along the effort.
Yeah, I do think there's kind of a history of that in this, open source silicon space of people doing things that others, especially industry professionals, say is impossible. Again, it wasn't easy for TNT to get that thing working, but he managed to do it, and that was pretty amazing. And I think out of those shuttles as well, we got a really cool thing called Tiny Tape Out, which TNT is also involved with these days. And, the story behind Tiny Tape Out, right, is that Matt Venn, who's the person, one of the persons behind it, was like, this is too much silicon area, right? I can't use all the silicon area, so why don't I get together and share it with some of my friends? And from that, he'd never done silicon before 2020. And now, if you go and look at Tiny Tape Out's website, they have had thousands and thousands of people, do tape outs and get back working silicon and working designs. It's like absolutely amazing that a person, 6 years ago who has no real formal training in ASIC development is now probably responsible for teaching more people than many people have had 20-year careers in this industry or 40-year careers in this industry. So I think this really shows what happens when you open it up.
Yeah. Matt did a great thing, and all the community that rallied around it and all the efforts combined made for some really exciting things. And people from all walks, from teenagers to veterans, they're all kind of hanging out, and they're collaborating, and they're making things happen. I mean, I really like the demo scene stuff that they did, which was really cool. They had some excellent demos that came out of it, and I think there's another one coming up.
I think the demo scene, for those who don't know, the demo scene has always been about making systems do things that people think are impossible. They make very obsolete hardware do things that modern hardware struggles with. And so Matt then said, why don't we do the same with like the tiny space available on Tiny Tapeout? And the great thing about those is that like you can only see blinking an LED so many times before it stops losing its impact, right? But like some of the demo scene stuff is like absolutely awesome to see, like visually, right? Like, and there's even a whole bunch of music. If you're into things like chip tunes and Eurorack synth type stuff, there's a lot of that happening in that demo scene space. And I highly recommend you go and check out the Tiny Tapeout demo scene URL, because there's a video there that shows you a whole bunch of it. They've done a really good job of a simulator so that you can basically run your like design and get a video of what it should look like when you output it. And that, again, is super impressive. A lot of that type of stuff normally costs you, tens of millions of dollars worth of hardware to get functionality like that. And, it's just amazing what happens when software engineers and people who don't know that you're supposed to charge all this money for these things get together and make things happen.
Oh, most certainly. Yeah, it's been a really exciting ride. So I guess from Tiny Tapeout and that kind of all the kind of things that were happening in the space, kind of how do we get from there to wafer.space?
Okay, so in by the start of 2024, Google had kind of ended the program around free silicon. And at that point, I'd left Google. I decided I kind of wanted to take a break. I've been working pretty hard for quite a long time on this open source silicon. And it seemed like the space was, going pretty well despite Google stopping to do the MPW program. We had two open source PDKs at that time. Global Foundries had worked with Google to release a second open source PDK called GF180 MCU that was manufactured in Singapore. And then a third foundry, totally without Google's help, called IHP in Germany, released their 130 nanometer PDK as well. And so we had a 3 PDKs that were open source, and we had things like Tiny Tapeout. Tiny Tapeout had dropped the cost of doing a tapeout down to, around $200 to do your first tapeout. And eFabless was offering a 10K to get your tapeout if you wanted to do something bigger than Tiny Tapeout. So that all looked good. But then at the start of 2025, due to some investor disagreements, eFabless collapsed. And, this is the issue with startups and things where you have outside investment, is that outside investors can choose to, they would rather see, their investment go away than it continue. And so eFabless disappeared. And at that point, I kind of went, well, I guess I'm going to have to do this myself. And that's where wafer.space comes from, is kind of like, okay, I'd worked heavily with eFabless to work out, how to do the $10,000 item, and knew how much things cost. And because I didn't work at Google anymore and eFabless was gone, it felt like creating a new one was a reasonable approach. And really, nobody had offered Global Foundries PDK as a manufacturable option. eFabless had only ever offered the Skywater one. And so I wanted to offer the Global Foundries one because I knew like Global Foundries process is a bit older, but it's also significantly cheaper than the Sky 130 process. And so I was like, well, I got out my spreadsheet and started, punching in the numbers. I had done a bunch of crowdfunding campaigns with Crowd Supply before, and one of the hard things of doing something like this is accepting money. And so I tapped them for, being the person who handled all the money type problems. And from that, I came up with this idea that I could do essentially what Google did for about $7,000 to get you back 1,000 chips, right? And I really wanted to continue this idea that you could use it as low volume manufacturing because normal like programs, MPW programs, forbid you from like selling your chips. And so even if you can afford to do the like tape outs and this type of thing through the traditional systems, until you go to volume manufacturing, you can't actually make a product, right? And that's always like, how do you know your product is correct when you've not shipped it at all? And so my idea with like 1,000 chips was that, well, if you get 1,000, you put 100 towards your like first prototype that doesn't work. You put 100 towards your second prototype, which finally does work. And then you've still got like 500 left to send to early customers, right? And like, you've done hardware stuff for a while, the idea of like, you want the resulting cost to be like 3 times the BOM cost, right?
2.5.
So, if you look at like $100 product, then the BOM cost should be about $30. And so a $7 part out of a $30 BOM cost is like a large part of it, but it's not outrageously part of that. And so the idea that you could sell 1,000 units of some type of product at $100 each seemed reasonably attainable, right? And if you needed a custom ASIC to do that, all of a sudden that felt possible.
Yeah, it wasn't possible before, so it's pretty amazing.
Yeah. And so that's where we were with the first run. We had the $7,000 option. And then what we realized is we could divide the slots that we have. A 1x1 slot is the $7,000 and it gets you about, I think it's 20 millimeters of silicon. We could divide that in half and that gives us half slots. And so in the second run, we had half slots. And with half slots, the price is roughly half. And so we had $4,000 slots available on run number 2. And you can kind of see where this is going in that then we realized we could divide it even further to quarter slots. And this is where we are on run number 3 is quarter slots for $2,000 if you get it in early enough. In the early bird pricing, $2,000, you get 1,000 chips, quarter slots, which is, $2 a chip. And at $2 a chip, right, like a $10 product or $20 product starts to become possible, right? Like a $10 dev board means you've got like a $3 BOM cost. A $2, chip is a big part of that, but it's not, all of that. So that leaves you some for, 50-cent PCB and some connectors and some other stuff, right? And so
you gotta bond it.
Really,
you gotta bond
it. Packaging still is a little bit of an issue. I do have an option that allows you to package chips at $1.50 each. I would like to get that down because it seems outrageous to me that like silicon, which is some of the humans crowning achievements. It's like up there with like sequencing DNA and going to space and the moon and things like that. Costs almost the same price as doing a little bit of wire connections, right? Like it feels to me that the packaging should be a lot cheaper. I'm working to fix that, and there's lots of people exploring options. Like we're exploring bonding the silicon directly to a flex PCB. And I think if you look at the PCB space, I'm kind of old enough to remember that the first PCB I ever got made was because the PCB house owned my supervisor at university a favor. They wouldn't talk to me otherwise, right? Like all the PCBs back then were call us for a quote. You couldn't like get anything like that. And things like OSH Park really changed that, right? Like OSH Park made it so that I could just get PCBs done. And that also, like OSH Park really helped things like KiCad exist, because why would you have open source tools for creating PCBs if you had no way to make PCBs, right? And so for people who understand that, I like to say, wafer.space is trying to do for silicon what OSH Park did for PCBs.
Very cool. So that's awesome. So I guess for the next part, we can kind of talk about, we got a question here. How we want to establish a viable supply chain for scalable chip manufacturing. So I guess that already existed, because the global foundries were just leveraging their factories essentially, right?
Yeah, the thing I'm trying to make it is that if you want 1 million of a chip, the current industry is able to do that, right? Like you just need to go and find the funds to do that. I'm focused on the people who only want 1,000 of a chip, right? And how do we make that happen? In the same way that, you could use OSH Park to get quite a few PCBs, but you're not going to get 1,000, like 1 million PCBs made through OSH Park. You're going to go and get them made directly from the manufacturer. You can do that with Global Foundries today, right? Like, as far as Global Foundries is concerned, I'm just a normal customer of them. You can order, if you've got the money, you can go and order from Global Foundries exactly the same type of thing I'm ordering. And because it's all going to be your chip rather than, 40 different chips, you're going to get a lot more parts per run. But that also means you need to sell a lot more parts per run, right? Like, if you think about it, I'm getting 1,000, chips per person, and there are 40 people. So like my run is 40,000 chips. And this is kind of the short, smallest run that we could do. Like in run one, I reduced the number of chips people were getting back to half the amount of chips. And it only saved me roughly 10 or 15% of the overall cost, right? And so that seems like a poor trade-off, right? And so that's kind of why 1,000 chips is the, units of the minimum unit. Going lower doesn't reduce the cost. One of the ways to reduce the cost further is to share between people, right? Like Tiny Tapeout, is a customer of mine now. I worked with a group to help Tiny Tapeout port to Global Foundries technology, and they are now running Tiny Tapeout shadow runs on wafer.space. So, like, or order $200, you can get a tape-out done with Tiny Tapeout on the same process technology that you can then move to a $2,000 option once you want 1,000 or something, because Tiny Tapeout only get you back one-ish chip, but that one chip is mounted on a dev board ready to go, right? Like and sadly all my dev boards for Tiny Tapeout are out the back being mounted so that you can access them online. But
Very cool.
yeah, the dev dot is really cool because like once you have a chip, you still need to like interface with it in some way, right? Like, and tiny tape out make all that go away.
Yeah, definitely. So I guess we could talk about what we can actually do with this process, like some example projects of what people have done so far, kind of where in time like this process is from. So like this thing came around at the turn of the century, right?
Yep, it's kind of 1999, 2000s technology. So
right.
don't expect to be doing a modern NVIDIA GPU as well. You know, a modern NVIDIA GPU is taking up that whole reticle space for just one chip, whereas, you know, we're dividing that by 40. But, you know, I'm amazed at what industry says can't be done with this, and then what people who don't know better do with this, right?
Yeah.
Like, as well, you know, to be fair of industry, Moore's Law was a powerful thing where, in many cases, why would you optimize something? Instead, you could just go to a more modern process node and for free, that for free is, you know, doing a lot of work, you get significant performance improvements, right? Like, and so that was kind of like a driver. And Bunny, who I think you know, and is behind another mostly open source chip called Bao chip. His RTL is open source, but he's targeting a more modern closed source PDK. His chip, you know, is on I think it's a 22 nanometer process technology, and his argument is that, you know, in a couple of years, if this AI bubble pops, you know, these chips are going to be these foundries that make this are going to be looking for new customers, and so for you know, we need people to be doing chip design and making all their mistakes on this cheap older node, right? Because even if these foundries, you know, have the capacity, it's still significantly more cost to do. It might be cheaper per transistor, but it has a higher NRE to do a 22 nanometer chip than 180, right? And so really, this is kind of like my first silicon is kind of the way I like to think about it. And, you know, once you've sold 1,000 or something, it's much easier to commit to a bigger NRE investment than it is when you've sold 0 of something, right? Like, I think I could probably, you know, if you look at my history, I've done a bunch of crowdfunding campaigns. $1,000 board, selling 1,000 of $1,000 board is a much harder job than selling 1,000 of $100 board, or, you know, selling 100 or 1,000 of a $10 board, right? I could probably sell 1,000 $10 boards pretty easily, and I think you probably agree with that. Like, as it gets cheaper, it becomes easier because, you know, people will buy a $10 board and throw it in a drawer and never use it, but that's fine if it means that this thing can exist, right?
Yeah, so I guess we could talk about a few of the projects that kind of fell out of the runs. So you have like it looks like 5 that you mentioned on your Discord channel.
So one of the really good things is the open source designs you can go and look at. And so for run 1, if you go to the GitHub and there's run 1 there, that has a whole bunch of open source designs. And then run 2, which has yet to come back from manufacturing, but is in the process of being manufactured, is also up there. Run 3, again, will be up there once that's closed. That closes at the end of the year, and that's the one you can purchase today. On run 1, there was definitely some very interesting designs, and they were the ones that I think you were going to highlight.
Yeah, so let me go ahead and maybe I can share, maybe not. We could just talk about the projects, I guess. So I guess the first one you mentioned was the Kane 5 Linux CPU. So we already talked about that a little bit. So that one was actually a Linux capable chip, well, MMU-less Linux capable chip on the first run, right? And then
so the history is longer than that. This Cayenne RISC-V, the history is that it was done by a single person, an embedded software engineer, and he started creating it in his spare time. And then he got an opportunity to put it on one of the tiny tape-out runs. And industry was pretty much, you can't fit a Linux-capable RISC-V in tiny tape-out. Like, tiny tape-out just isn't big enough to have a Linux-capable RISC-V. As software engineers, we know that, like, people put Linux on pretty much anything. It might be a bit slow, but it's definitely possible. And so he managed to fit Linux, the MMU-less Linux, on a tiny tape-out. When he had more space on the first wafer.space run, he was able to then upgrade to full MMU capable Linux. And so if you go to the FOSSI Foundation's El Coro Libre, I'm just sharing my screen here with a little picture of it. So this is the board. I don't know if I can make that bigger. This is the board. You can see the little chip here in the center, and it's got, standard SD RAM. And this is a full Linux capable chip, right? It has MMU. It's a RISC-V 32-bit. It has like SD card for storage. It's all the fully open source. And, it runs a little bit slow. I think it's about 25 to 50 megahertz-ish type range. But again, this is done by one person. With a little bit of help from the community and that type of thing. But the other really cool thing about this is that it's, running upstream Linux. It doesn't, need one of these vendor board support packages. His day job is an embedded software engineer. And so he was like, screw this, I don't want an out-of-date kernel with custom patches. I want this to run upstream Linux. And so you can go to kernel.org, download the Linux kernel, set the right config flags, and it will boot on this machine, which I think is pretty awesome. This is kind of like, I would say, Raspberry Pi 0 level, Raspberry Pi 1 level-ish, and it works. This thing up here, this dev board has booted, and he's had Ethernet connected to it and that type of thing. It's pretty cool. There's still huge rooms for improvement as well. As I said, this is mainly one person doing this work. He didn't start with a existing RAM controller or an existing MMU or existing, RISC-V. He did all that himself in his spare time, in about like a 2 to 3 year process. Normally industry says you need like a team of 5 to 10 people to do something like this. And maybe to get something that is, pushing the limits of what you can do on this process technology, that's true. But ultimately, this chip is only $7,000 to get made, right? How much performance do you actually need? How much testing do you need when, at worst, you've wasted $7,000? I mean, $7,000 isn't, a small amount of money, but it's not $7 million, right? I would much rather lose $7,000 than $7 million if I was you, right? That makes things a lot easier, right? The amount of testing you do, go back to tiny tape out. At $200, how much verification do you need to do? You can tape out and try it, and if it works, good. If it doesn't work, you've only lost $200. And the great thing about tiny tape out is you get everybody else's project. So even if your project doesn't work, you can play with a bunch of other people's projects. And taking risks as part of learning, right? Like just doing safe things is really boring, and not how you learn how to do things and what's possible. And so that's what's really cool about making this stuff cheap and easy, is you can take more risks, right? You can try things, and if they don't work, oh well, you haven't broken the butt. You can try it and see if you like it. Silicon design isn't for everyone. I'm perfectly open with that, but everybody should try it at least once, because it is one of humanity's crowning achievements. And the fact that you can now, have an attempt at it for something that a cost of a nice meal in San Francisco, I think that's pretty amazing.
Very cool. So that was one of the key stone projects, or a project that was really pretty awesome to see. I guess the next one was I think it was Tiny QV, which was a crowdsourced MCU, which is really cool. I'd like to hear more about
I'm sure you've had this problem of that, you've gone to find a microcontroller and you're like, well, I need 4 SPI buses and 2 I2C buses or something like this. And the only thing on the market is something that doesn't have the right set of peripherals, right? Now, if it makes sense, you can create your own with the right set of peripherals. And this Tiny QV crowdsourced basically hundreds of different peripherals that they wanted to put on this device. So it has weird things for interfacing with NES controllers and PS2 and all these other protocols that you wouldn't think you need to exist. But that's one of the really cool things about this, is that you can do that because, again, it's cheap enough. And this was done through a tiny tape out competition where they put all these peripherals on a tiny tape out test to see how many peripherals they could get on there and how many they could test. And so I think that's a really cool example. Mike Bell, the guy behind Tiny QV, I think is really awesome for doing all of this. He's also done some really other cool things in the space. Here's the reason that, for example, the tiny tape out dev board can pretend to be SPI RAM. So again, it's kind of one of these people who is doesn't know that you shouldn't do these things and these type of stuff, and just does it. And so, I think that's really cool that when you open it up, these people do this awesome stuff, right? And now you could potentially take some of his work and create your own chip that has just the peripherals in the makeup you need, right? And that's kind of cool. And if that means that your device can exist, whereas previously it meant that it doesn't exist, or it uses less power, because, I'm sure we've all had the case of having to bit bang a protocol rather than have a hardware for it, because even if the hardware's there, it doesn't work properly, or it's connected to the wrong pins or something like that. Bit banging something is so much more power hungry than having it in hardware. And so this might mean your thing can run on battery way longer, or something along those lines.
Definitely.
One of the really cool things on this peripheral space as well is that you might be familiar of the PIOs in the Raspberry Pi Pico.
Right.
Bunny has been trying to make his own basically version of that, which he taped out in his advanced chip. He also got somebody to tape out that IO standard on run number 2. So on run number 2, somebody has taken basically the design, and so we have that BIO design now on both an advanced process node and on an older process node. So it'll be interesting. Hopefully that works. As I said, we haven't got run 2 silicon back yet, but they'll be super interesting to see, like, also how the performance changes there, right? And the great thing about that is that if it does work, anybody can put that in their chip. Like the
Cool.
PIO is a proprietary design. You can't take and put a PIO from Raspberry Pi in your own design. So I think the BIO is an interesting thing from that type of view. And like what you can do with these little programmable engines is amazing. I think I first saw this type of concept with, I think it was like the BeagleBone has its, these little, similar type of idea, right? Is having a little controller that can more efficiently, access some of the I/O and that type of thing. So, that's always been a cool idea. It's just never really been accessible. I think Raspberry Pi that showed when you put it in the hands of people with the right set of documentation, they can do crazy things with this. And so this is obviously the next step is like, well, why don't we make it open and available for everyone's ASIC so that you can put it in your own ASIC?
Yeah, and for people that don't know, it's actually based on the Pico RISC-V core from Claire Wolf, and it's very small. And for the higher end architecture, he has a VEX core coupled with it, right? How are they doing that on the kind of the trailing edge or the trailing edge node that we're using, like the 180? Is it just?
I have no idea. You'd have to go and look at it.
Okay, so maybe we'll have to dig into that on in a future.
I think it might just be the I/O core. You don't get the higher end RISC-V with it. So maybe it becomes an external chip connected to a more powerful chip, but I'm not sure. You'd have to go and look at it, and the design's all there. You can see what it is. And since we're kind of talking about tiny cores, Pico RB32 at some point was considered a tiny core, but I think these days we would consider it a medium-size, MCU core, because you look at things like Olaf's Serve core. Olaf Serve core, you're starting to count the number of, flip-flops in hundreds, right? Like you can individually count them. And one of the really cool things is on, let me see if I can remember the URL. So there's a guy who I think you probably know as well, called Greg Davil, who actually happens to be from my hometown of Adelaide, which is where I am these days. But he did basically a tape out of the serve core, and because the serve core is so small, he can fit, let's see, no, that's the presenter view. This is his presentation from Down Underflow. So he first did the serve core on tiny tape out, again following my idea that you should put the serve core on tiny tape out. He did this on one of the free Google runs, and you can kind of see here, if you look closely, this block here is the SRAM. This block here is the CPU. Like the SRAM to hold the register file for for the serve core is bigger than the logic you need.
Right. That sounds about right. It's bit serial.
Which, tiny. Yep. So he then went, okay, I've got a friend who happens to do silicon. Maybe we can put it in there. And so this is an example. And he did variants of all these ones. So you can see this is a full size slot. These are the two options for the half size slot, and here's the quarter size slot. And this one here, I think, has 28 RISC-V CPUs on there. And the reason it doesn't have more isn't because there's not more space. You can see there's actually quite a lot more space, but because he ran out of time. And so I'm pretty sure he can fit more in there if he starts being smarter about how he packed it. But even on the small design, right, the quarter slot, he has 2 RISC-V CPUs in there. And okay, that's slow RISC-V CPUs, but it's still pretty amazing that you can get that many cores on this old silicon in this space, right? Like, it's definitely a case of, again, what can you do with this process technology? Well, there's a lot of things people think you can't do that maybe you can. And so, yeah, and this is all, available now. You can use this. Here's another example. Here's the memory again, and this is all the, gates needed to do the rest of the system. You can see it's very tiny. And so I think that's a super cool example of, again, a smart person doing something cool because they have access to do it.
Yeah, and I know Greg pretty well. He actually helped with the Pi5 project. He did a FPGA design for us that we used to develop CircuitPython implementation for our intended end game was CircuitPython microcontroller. And we had that all working on an ECP5 FPGA board. But yeah, we never got off the ground with the whole thing. I mean, we can come back to it, but it's like, it just kind of faded into the background. I might bring it back. It's just a matter of finding time. I had to.
Yeah, I'm pretty sure Greg has Zephyr and MicroPython working on that one.
Yeah, it's a lot easier to get MicroPython running, but CircuitPython required a little bit more USB, and it needed a high resolution timer as part of the kind of core functionality and interrupt stuff. And yeah, it was possible. I think we could do it. It's just a matter of putting in the effort. I mean, you got Linux running on the thing. It could run CircuitPython, no problem. I think the big thing was finding a productive place for your heap, because you cannot put a lot of RAM in these things. And modern, people want more RAM than you can provide, essentially. So our idea was to use PSRAM as kind of the heap for the core. And I'm guessing the Cayenne project was using DRAM, maybe SDRAM for their.
Yep, it's using SDRAM. I don't know. The original Tiny Tape-Out ones used PSRAM and SpyFlash for and it used execute in place SpyFlash, I believe. I think there's a lot of work we could do to improve that. The SpyFlash, I'm also looking at how we could potentially do the co-packaging, because one of the things that is limiting of this technology is you don't get a lot of SpyFlash, you don't get a lot of SRAM in a 180 nanometer process. But if we could take something like an off-the-shelf 45 nanometer technology and put it in next to your custom ASIC, all of a sudden the economics change. And this is kind of like a very budget, cheapo version of what the high-end NVIDIA guys are doing with stacking HB RAM and doing disaggregated, chiplet type things. It's the same type of idea, but doing it at the very low end, trying to make it cost reduced and have low NRE.
Okay. So yeah, I guess we can talk about the Ethernet switch ASIC real quick. And I think that was the second to last one that we wanted to go over.
Yep.
And the fabulous FPGA.
Yep. This is the open source Ethernet switch. Again, one of the challenges is making it work with the limited amount of memory available on these old technologies.
Right.
But if you know how a switch works, you could do pass-through, and so you don't need to buffer everything. The store and forward approach is what modern switches use because SRAM is mostly free for them. But you can do other like cut-through approaches, which means you can get away with a lot lower SRAM. And Essen, the person behind this, is really great at writing up all the stuff they do. So I highly recommend her blog about all the stuff she's done. She's another one of these people that just does lots of cool random shit, like has reverse engineered cheap FPGA cards off eBay and stuff like this. She has an AI array that she's done in Tiny Tape Out and various other things like that. And
cool.
yeah, the Fabulous chip, I think, is probably worth a mention as well. This is a fully open source FPGA on, an open source ASIC. It's a bit small at the moment.
I think it was.
Yep. But one of the cool things is that it can switch between 16 different like images using a boot time thing, and it has a bunch of stuff like register files and hard multipliers and stuff like this that normally you wouldn't get with such a small FPGA. And so again, if you look at that design, you can see there's still plenty of empty space. So I'm pretty sure with future optimization, we can get this into, the kind of 1,000 to 2,000 LUT4 range. And, that then starts to become potentially competitive against things like the ICE40 type chips, where you have a fully open source ASIC that you can expect and, customize to your own needs, right? Like, that's the other thing, is that at this price point, instead of getting, 1,000 ICE40s that are all exactly how some designer 20 years ago thought that an FPGA is, you can customize it exactly for however you're going to use it.
Yeah, but by the time you get to an ASIC, FPGA kind of, you push to the side. You've gotten your design and you're ready to make something that's...
Well, like, that's the thing, is that maybe this is the approach of, like, you just harden only a very small part and leave the rest in FPGA, because then you can change it, right? Like, you can speed up the iteration time. That's one thing, like, as a software engineer, I hate about the Silicon world, is that, like, it takes you 3 months per iteration at a minimum, right?
Yeah.
And so that's really frustrating. But doing things like an FPGA, I think, really could speed up a lot of this.
Yeah. Okay. Yeah, definitely. So I guess that kind of does it for like the showcase projects. I guess we could talk about the upcoming Chipapalooza and what's going on around that. There's a new challenge that opened up recently. It's an analog design challenge for the analog nerds in the audience. So that might be something we can talk about. Do you know anything about it?
I'm more of a digital person, so I don't know much about it. It's run by Tim Edwards, who has been doing open source silicon for much longer than I have. Some people like to say I'm a grandfather of the open source silicon stuff. He would be like a great grandfather then. He's definitely been doing a lot of this, and he's doing a lot more harder stuff. Like, mostly what I'm doing is filling out paperwork and doing spreadsheets to enable other people to do interesting things. I don't do any of the interesting stuff myself. But that's I'm in a position where I can do that, and I don't need to take, for example, outside funding to make sure that the company stays in my hands and doesn't collapse because, except anything I do, I'm solely responsible for that. And so, that's kind of the cool thing about what I'm able to provide. And the rest of the people are doing cool things on top of that. One of the best things about this is that I come across people all the time who have done cool things that I've never heard about, right? Like Tim Edwards didn't need to ask me to do Chipalooza, right? Like, he can just do it. Right. He can, right? Like, you can just, if you have a crazy idea and you can find the funds to do it, you can just do it, right? Like,
yeah, and I guess they're funding a run on this shuttle, right? Round 3.
I believe so.
Very cool. So
and you can see kind of the deadline for the current run 3 that's happening right now.
Okay.
So you've got, 41 days to get the early bird pricing, and 118-ish days to get your design ready for submission.
Yeah, if you're thinking about doing it, 41 days will go by really fast. So start early and get your ideas from paper onto, it's gonna take some doing. So don't.
Yeah, I do think, like, again, it depends on what you're doing. I think Ezen has shown that if you drink too much coffee, maybe you can do it in a week or two. Again, it's a risk versus reward as well, right? Like, if it's not costing you anything but your time, how much time are you willing to dedicate to it, right? Like, I think that's a big thing, is like, a lot of people say, oh, you need to test this really, really hard. Well, you do if you can't afford to lose money and can't afford your chip to come back not working, right? But, if you can afford for your chip to not come back working and you can do multiple iterations, then maybe you don't need to test it as much.
Yeah, definitely. Well, you still want to test it, and you want to try to run some verification on your stuff.
Yes, but again, like, I met somebody recently who was like, I no longer do design reviews on my PCBs because, like, it's cheaper to send them off and get them back in like 3 days later. That when I get them back, I can just do the footprint match with the real PCB, not having to get out printing, figure out how I get my laser printer out and like print it out and try and put them on. I was like, my time is worth more than the cost. Like, it's costing him $5-10 to get the PCBs done. So, the time it takes to get printing working on Linux, maybe is more than it takes to, get the PCBs done and things like this, right? Like, again, it's a trade-off, right? If you're a software engineer earning a Silicon Valley salary, maybe the idea that you can just throw some shit at the wall and it comes back and doesn't work isn't such a problem. You get a shiny result. Oh, and something I didn't mention is, people are doing really cool, like, artwork and stuff like this. I think we saw this with Osh Park, is that, like, once it's open to everyone, people will do non-traditional designs. Like, some of the coolest looking PCBs out there come from, people doing, stuff. And like, I bet you if you tried to do that back before, when it was quotas type thing, they would have said, no, we're not even taking that job, right? Like, and so like, I know some people who are trying to do like earrings with silicon in them because, at $2 a chip, it's, doable for just an art project.
Wow. Yeah. Alrighty. So I guess we've kind of come full circle. Good time to start fielding some questions because we're at the hour now. We can go a little over today. We've done this in the past. And we can take questions now. If anybody has anything, let's see what you got. Oh, there's one from Delta. So that was Delta. Kevin was actually in the behind the scenes earlier in the show. He was going to come on and talk, but I guess he dropped. But he's asking about.
So to build even 180 nanometer foundry, you probably need to get at least $500 million to $1 billion to kit out that foundry. And so the cost of doing like a traditional foundry is very expensive. There are some people doing some cool things called hacker fab. They're targeting like a 2 to 1 micron process technology. So, that's more late 1980s technology. I also think there's some cool options where maybe you do a what's called a gate array with wafer space, and then you put a final metal layer on which is 1 micron, and because it's the final layer, it can be a lot coarser. And the hacker fab stuff is in the $20,000-ish to $30,000-ish to build a little silicon line that can do maybe a 2 to 1 micron process. The kind of cool thing about that is at that price, it's probably not worth having things like a clean room or these type of things, right? Like one of the things that makes it really expensive is that you're trying to reduce defects, right? If you're only doing a small number of stuff, maybe a higher defect rate is 100% acceptable, right? Like, and again, this comes to cost versus reward. If you're making, $1 million or something, having a high defect rate is probably not good. But if you're making 100 or something and 10 don't work, maybe that's fine, right? Like, and that's a 10% failure rate. And so, like, doing this, and especially like the cool thing about the hacker fab stuff is that you could have a turnaround time of, days for a lot of the steps. And, so that's cool.
Yeah.
And like a lot of that come up.
I was just going to say that I don't think people are making the silicon at home. They're buying like.
I would definitely say that it's one of the more crazy ends of it. But a lot of this hacker fab stuff is inspired by a guy called Sam Zieloff, who is somewhat famous for being a high schooler who did silicon in his garage. The hacker fab people were a little bit frustrated that they weren't able to easily replicate that. And so one of the core principles behind hacker fab, if I understand correctly, is they want it replicatable. And so they have multiple fabs, like these mini fabs that they've been putting together at multiple locations so that they can prove that they have a, reproducible process for doing this, right? They can, for things like spin coders and stuff like that, they have an open source spin coder that they use. They have an open source lithography system that's built from a, I think it's a TI projector guts type thing. They're doing some very cool stuff.
Okay, we got another question. What is the software needed? Okay.
There's a template that we have on the website. My goal, though, is to not provide design support. If you go to the template, though, it uses a thing called LibreLane. In theory, you can put your RTL written in like Verilog, and it will produce a DRC clean GDS out of that you can submit. There's a pretty active community on Discord as well that can help you in various different ways. But just like OSH Park doesn't really provide design assistance in making your PCBs, wafer.space is not in the thing of doing the stuff. If you can produce, like, if you draw it manually in Inkscape and it passes DRC rules, we will manufacture it. I don't suggest you do that, but if you want to, there's options there to do that. And Tim Edwards, who does the Chipalooza, maintains a program called Magic. Magic is so old that it predates open source, and it's older than I am. I think 1982 was the first release of Magic. So, that is a very old piece of software that is still in active use today and in active developed by Tim Edwards. He didn't, create it. I'm pretty sure he's not that old. But he's the active maintainer of it today, which is pretty cool.
Yeah, it's been around a long time. Back when I was in school, it was around, and yeah. So I guess we could. There's like, I guess, a container or something that you guys have provided, where you can download and
Yep, there's a couple of different container options. There's a couple of different approaches where the build happens entirely on GitHub Actions, that you don't do anything locally. You just use the free, compute resources Microsoft provides through GitHub to do the work.
Right. Which is good.
There's a lot of different options.
Yeah. If you're going to do it something a little more complicated, you're going to need a pretty nice machine with a lot of RAM, and you're going to need I don't know, really high-end processor, single core.
Yeah, but again, it scales, right? Like if you're doing a tiny tape-out one, the tiny tape-out ones can run in GitHub Actions in under 5 minutes because they're so small, right? Like,
yeah.
But if you're doing, a full 1x1 chip, that can take hours. Interestingly, if you're a gamer, your high performance gamer CPU is actually very good at doing EDA stuff, because a lot of it's single threaded these days. And actually some of the people doing development have been, renting these gaming, cloud machines that are designed for like people who want low latency, high performance gaming stuff. It's kind of funny. It also, like, game developers have done some very cool visualizations where you can fly through, your GDS and other things like this. I definitely think there's a lot that can be cross-pollinated. And, a lot of games like Factorio and what is the name of the... he's a guy who does a lot of these type of games. Zachtronics. A lot of these games have a lot of similar principles to what actually goes into making this for real. That's pretty fun, I think.
Definitely. So do we have any other questions out there, Fixer? I think that's it. Okay. So before we call it, I'm going to have Fixer come on, and he wants to talk about a competition that is underway with the devEco. So thanks for coming on and sharing, Tim. And it was really fun, more exciting than our usual episode. So it's been fun.
It was amazing. It was amazing, Tim. Like, I've never seen that side of the hardware space, to be honest. Like, I've talked to Michael a million times, talked about supply chain, like sourcing parts and making sure that you build from the PCB layer, right? But I mean, it's pretty cool. So I actually plan on checking out wafer.space quite a bit moving forward. Thank you. Do you mind sticking around while I just do a really quick plug?
Sure.
Awesome. Okay, so everyone, just so you know, devEco.io dropped open beta beginning of this month, and with that came a contest sponsored by Qualcomm, Arduino, and Edge Impulse, of course, backed by the Edge AI Foundation. I'm going to share this real quick here for anyone who's interested. This is the platform just launched. It's the first contest. We're figuring stuff out, so we kept it regional, meaning it's in the US. We don't know how to ship. We're figuring all these things out first, right? So putting it that way, here's the contest link. It's up top there. I'm going to share it in the chat as well. There's 50 Arduinos up for grabs. So you submit a proposal. If your proposal is in the top 50, you get an Arduino. You then take 2 months to build out your proposal. And the winner of all of this, I hear it's in the several thousands of dollars cash. So one winner gets quite a nice little chunky sum of dollars. And hopefully we end up seeing you at one of the Edge AI Foundation events as well, to showcase your stuff that you built and along with some of the Qualcomm outlets. But I'm going to put this in the chat. If you have any questions, you can drop into the devEco. You can go check out the devOSH hub on devEco.io, and look forward to seeing some cool stuff being built. Let's put this in. And I want to plug one more time here. Make sure you go check out wafer.space. I was looking at that.
I've been trying to get some branded waffles as things that can be given out. Some Stroop waffles. They kind of look like wafers.
So you have a competition going, Tim?
So it was my competition, as in alternatives to wafer.space. Like one of the things that I do want to, talk about is that with eFabless collapsing, it became important for us to say, well, look, we want multiple different options for people to make their chips, right? And so wafer.space manufactures with Global Foundries in Singapore. So we kind of consider us an Asian-based solution. Chip Foundry, which is kind of like the people from eFabless resurrecting manufacturers with Skywater in the US. So I see that like your competition is, more resilient America type thing. If you want to do open source chips wholly manufactured in America, Chip Foundry is your option there. And then if you're in Europe we have IHP. And the cool thing about IHP is that IHP is the foundry directly. You're not dealing with a third party like Wafer.space or Chip Foundry. You're dealing directly with the people who make your silicon, which has its pros and its cons, right? So I definitely think that's what's exciting here. And Tiny Tapeout takes advantage of this. Tiny Tapeout targets all three process technologies. And one of the cool things I've done is that a tile on Tiny Tapeout fits roughly the same amount of logic on Wafer.space and IHP and Sky 130, even though they're quite different technologies. And so you can have a design, especially if it's a digital design, that is fairly easily portable between these different technologies. And that, I think, is super cool, is that, like, say I get hit by a bus, wafer.space is probably not going to survive at the moment. I'm working on, contingency planning for things like that. But there are other options out there, so we are not in the same, space where, eFabless collapsing removes the ability for, people to do silicon manufacturing. And, I would say Chip Foundry is a more premium service. It's definitely a little bit more expensive, but they do things like try and get you back a full dev board, which Wafer.space, being the budget option, I'm focusing very much on reducing the cost as much as possible, doesn't provide you with. So, they also have a much, if you just want a cookie cutter type, I don't want to think option, Chip Foundry is also doing a lot of that type of space. And so, I think that's cool. There's some other groups, there's a UK group called Pragmatic IC that has said they're going to do something. They haven't released anything yet. And that Open SUSE group that you kind of highlighted, that's a Japanese group. They have a small process that they're experimenting with as well. So I think it's kind of exciting is that there are lots of options. And I think open source is showing that you can be a lot more portable than you could in the past. Like previously, if a design was done at one foundry and that foundry decided to stop making that process, you no longer got that design. And that's what happened with the Z80. And a bunch of people have recreated the Z80 on wafer.space, like the GF180 MCU technology, which is pretty cool, right? Like the fact that somebody can do that is now possible.
So Tim, real quick, by the way, thanks for sharing this. I'm looking at the chip foundry, and you mentioned though that if you disappeared, right, that wafer.space would not, it wouldn't be able to survive, right? Like this is kind of one of the things that we wanted to tackle with this project platform, right? That we're talking about the contest is we actually built this open sourced and federated. So we have other prop up instances. So if we disappeared, right, all the users' content, it belongs to them. It's there. It can be recovered. It's all there. And so like I'm curious if maybe that's something
so like
consider.
Wafer.space, the company might disappear, but like the platform and the tooling and the PDK is all still there. So like an alternative to wafer.space could pop up if they have the relationship with Global Foundries, right? Like at the moment, that is the core value proposition is that idea with Global Foundries for you. Global Foundries is, I forget how many billion-dollar company. And so, dealing with that is, let's say, not the easiest. And, same with like Chip Foundries. Chip Foundry deal with Skywater for you so that you don't have to try and interface with a company that is mainly used to having, orders in the hundreds of millions of dollars type, space. And so like there could be more of these companies pop up. There's a foundry in, I think it's Malaysia called Silterra. Malaysia could launch their own wafer.space like thing using all the same tools targeting their local foundry. And we could have another, open source thing. But like there's nothing stopping people from doing this except the relationships and the willingness to, lose the money, right? Like this is kind of like the, if there's a screw up, right? Like I'm out of pocket, 200-ish K-ish. And so there is a bit of a financial risk there. But I've been lucky enough that, working at Google for 16 years means I have a reasonable retirement fund that I can use to, backstop that type of thing.
Your altruistic ventures.
I'm not trying to make it altruistic. Like it's a for-profit company, but like I don't want to make it. I'm not going to become the next trillionaire doing this. I'm trying to make sure it doesn't lose money, right? Because that's one problem is that like OSH Park, if OSH Park lost money, it wouldn't still exist, right? Like, and things like this, right? If you're like a lot of the access to silicon used to be through places like Europractice and Moses. These places, though, only exist at the whims of government grants. And, all it takes is a change in government that doesn't see silicon as important for whatever reason, and these services disappear. Whereas like a for-profit company only disappears if people make poor decisions about how they manage their money, which I mean, lots of companies do. I mean, there's whole, division about that.
I actually have a question about this. So let's say, for instance, you're running this contest, but I want to put it into a frame that I understand. So if you were to say, I am going to put this forward and see if I can rally 10 or 20 of the best ideas, or even 5, the best ideas for chip designs that you certified judges say, like, these are 5 great chip designs. How much money would you need to like get these 5 winners to go compete against each other? Like they pitched you these 5 chip designs, and then now you're taking this on. You're saying like, okay, I'm going to get these 5 people over the line, and I'm gonna see if they can these chips actually do what they say they can do. Is that even?
Well, they just buy $7,000 from me to get 1,000 of their parts back, and right, I don't even have to be as far as the people running that competition, like they can be just a customer of mine, right? Like they can just buy the slots and yeah. Yeah, 7K per person if it's like a big one. If it's a small one, like if they're doing the small one, then it's 2K per person. You probably want to put packaging on top of that, which is an extra 1.5K. So, say 10K per person is a good estimate because,
How long do you think this contest would need to run for to actually get these folks in
3 to 6 months?
3 to 6 months? Okay.
There's a group. I can never remember. So there's it's either I think it's Hudson River Trading is running a competition where you basically do something around ASIC design, and there's a couple of other groups that are trying to do chip related stuff and are trying to find recruits and running competitions like this. So and I believe Chipapalooza, I don't know how you pronounce it. They bought a slot from me to do the silicon run for their competition, and they're putting multiple projects on one chip, if I understand correctly. So kind of like tiny tape out, right? Like really, if the designs are small, it's only $200 per person then to do them on tiny tape out, right? Like
if you wanted a finished thing, you're trying to get these people past finish line, they get the chip, then you need some sort of PCB fab, right? So it's a PCB fab.
Yeah. So
you need the components as well. So a DigiKey type thing all comes together, arrives assembled after the design.
So that's what tiny tape out provides you, is the actual dev board, not just the chip. For wafer.space, it's your job to do that yourself. You can take examples from other people. That's the great thing about open source, right? If you don't change the defaults, you can reuse a lot of the existing PCB designs people have done, right? If you started from, say, Hirosh's Linux design, right, you could probably reuse his board.
I want to do this.
You need to get it manufactured yourself, right? I'm not in there's plenty of places like JLPCB, PCBWay, Next PCB, right? The Next PCB I'm actually talking with about trying to add wire bonding to their Rev 0 service, so that we can send basically the ASICs on consignment to Next PCB, and then you can just put it in your PCB like any other thing, and they'll wire bond it as part of that service. And then
will you be at SuperCon this year?
No. At the moment, I'm not traveling to the US, but if you I was at the Hacker Day event in Europe recently, and I'll probably be at other events. I was recently at COSCUP in Taiwan. COSCUP is kind of like, do you know FOSDEM?
Yeah.
Mm-hmm.
Yeah, it had a very FOSDEM feel. COSCUP was great. I really enjoyed it. I highly recommend if you're in the Asia region. If you're in US, Teardown and Latchup. If there's a conference called Latchup that is pretty much heavily focused on open source ASIC stuff. I think that was in Canada. But it's definitely in the.
Sure.
Yeah, I think that's the hack a lot of people are doing at the moment for a lot of these problems. But yeah, there's so many things going on now that it's impossible to keep up with everything, which is the way I like it, because AI has also had a pretty big impact here, in that a lot of this knowledge was very hard to get access to previously. I wouldn't trust AI to give you exactly the right thing, but it definitely helps to be able to ask it all your silly questions, right? And get some hints on where to look and where to find and follow up on these type of things. Because like this industry has been so closed for so long that like in many ways, like a lot of this just isn't knowledge, like the knowledge cliff where they stopped publishing academic papers is kind of like the mid 1990s. All the advancements since then have been locked up. And so we've still got a lot to learn and a lot of improvements to do.
Tim, I hope you don't mind, but I'm going to be talk about some stuff with Michael here, but I really want to run possibly the idea of wafer.space, tiny tape out, next PCB, some distributor of parts, and like trying to get some sort of really cool contest going where people are building this hardware from the ground up. I think that would be pretty awesome. 2027.
Yep. I mean, I'm very supportive of that. And the great thing is, if I'm not, you just pay me money and I'll still do it, right? Like that's the great thing, right? Like if you can find the sponsors that can provide the money for manufacturing, I don't care what you're doing or how you're doing it, really.
Well, it's great you're already talking PCB. I love Next PCB. The folks over there, like I advise for them. I root for them big time. So I'm glad that you're already talking to them because they're great people.
Yeah, the Rev Zero, human in the loop thing, I think has been the most attractive part. Definitely, we've had issues with other groups where every time we order something, it comes back slightly different. And, that's frustrating. I think that will be interesting. I hope I can make this wire bonding stuff happen. It'd be really interesting to have that, not just for, wafer-space ASICs, but so that you can get other things wire bonded as well. It can reduce the cost and make things a lot smaller. And it's like something that the big guys have had access to forever, and it hasn't been access to the average person, despite it being, a super old and reasonably cheap technology.
Yeah.
Where people connect, I feel like some of the coolest people connect at that kind of convergence of trying to help the small guy, right? Like, I mean, it's like data, wire bonding, chips. It's just like so many things.
Yeah, and again, I think it will be people do things that everybody was saying this is a stupid idea, and then they'll do it and show, actually, no, it's the next X or the next Y. Or
if it wasn't, if it wasn't confusing to someone else, if someone understood it, it would already exist.
Yeah, like that's the thing I always say is like, if the good idea didn't look crazy, somebody would already do it, right? So you need to make it cheap enough that these people can try these crazy things. And like most crazy ideas are crazy. Let's be clear about that. But some of them, a small percentage of them aren't, right? And they will create cool things when that possibility is available.
Oh, I'm glad there's another crazy guy in the room. Michael, did you want? Do we have anything else on this one? So, by the way, this is
no.
Okay, because usually it's an hour long. I usually say people.
About an hour and a half this time.
It was nice being behind the scenes.
Yeah, I don't think I've ever had a short interview.
Yeah, I think this was a fun one.
It was really fun.
But we should probably close it out at an hour and a half. So that's like right about now. So yeah, it was fun having you on, and it was good conversations. So we might have some Libre Silicon challenge coming up, is what it sounds like. So look for that. Let's see how it happens. See what happens, if anything. So very cool. Thanks for coming on.
Oh, I want to thank real quick. Thank you so much, guys. I appreciate it. It was rad. Really great show. Thank you. Wafer.space. Go check it out.
Yes.
Yep.
Use it or lose it, right?
Yep. And tiny tape out. Definitely. First, start with tiny tape out. And once you've done a successful ASIC, go to wafer.space and make an even better successful ASIC, right? Like,
yeah,
$200 is not that much to see whether you like it, right?
Put them all over the place. All right.
Oh, yeah.
Great, everyone.
Cool.
Thank you.
All right. Have a good one, everyone. Bye.